Hello friends, we are very much familiar with the term polynomial. Keeping that in mind, I am preparing this particular video where I am going to illustrate a very important thing related to polynomial or linear polynomial in connection with that of linear regression. We will see that. So right now what we have got over here is a very simple polynomial expression in the form of 2x plus 1. Why it is polynomial? Because it has a degree of 1. Okay, so x raised to the power 1, the degree over here is 1. Now I wrote a very simple function over here which is going to take a parameter and will return a value, and inside this I have written 2x plus 1, that is just like what we have over here in the form of polynomial expression, and the resultant value will store in the variable y, and then I will return it back. And for this I want to perform this process repeatedly, so I have written within a range where the starting value is -3 and will go up to 4, but 4 is not inclusive, as we know that. So basically I am going to pass individual scalar value to this particular string statement or to this particular function. Individual, like first time I will pass -3, then it will be -2, -1, then it will be 0, then 1, 2, 3, and this way I will pass, and eventually return me the result y, and that's what I'm going to print over here. So I'm passing a individual scalar value, and I'm going to see what will be the output in context to this particular polynomial expression. Very straightforward program it is, right? So let me run this particular program. So Python space linear underscore polynomial, no, file name is called linear poly. So I hit the enter now, and we get to see the corresponding scalar values. So I pass x as -3, which I said, and the corresponding, after calculation of this polynomial expression, I will get the value as -5, -2 is -3, -1 is -1, 0 is this, 1 is this, this is this, and so on and so forth. So from this what we can say? Well, if we write this in the form of y equals to this, we are calling it as a linear equation, right? Because we are going to do a comparison with that this particular linear expression will be able to evolve or able to create the following y value, and they are both left and right are going to be equal. So from there we are saying it's a linear equation. Now when I put this particular polynomial expression in the form of function, we call it as a linear function. Great. Up to this it's all fine, but we have to move to the next segment, and for that reason slightly we are changing our presentation now. What I'm going to say is, can we represent this particular polynomial in this particular form, w1x plus w2? What is this w1 into x plus w2? Well, x is the value which I am going to feed. These are independent values, right? So it will be -3, -2, -1, 0, 1, 2, 3. This is the independent value which I am going to feed for x. What about w1? Well, w1 is the weight, or we can say it's a coefficient. So this is 2, which is a coefficient, so I'm calling this as w1. This is a weight associated to this particular variable, isn't it? So we are calling this 2, which is a coefficient, to be as a weight 1, and this particular constant value as weight 2. So we can write in this way also, w1 into x plus w2. Remember, x is going to be the independent value that will be feeded, like what we are doing over here, -3, -2. These are all weight, these are all independent value for the variable x. But what is constant? The coefficient is constant. So w1 represents 2, so it will be 2 into x plus, and w2 is representing 1, so it will be 2 into x plus 1. If we write this, what actually happens now, right? And that is what giving birth to something called linear regression. How? Well, let's think in this way. I know, I have from here what we can see, I know what is the independent observations, like -3, -2, -1. So these are independent input which I am going to give for my variable x. I know this, and even I know what is the corresponding predicted value that is going to come in context to y, like -3 when input will be -5 when input will be -3, or -3 will when input is -1, -2, and when it's -1 as an output when the input is -1. We know this, right? But just for the time being, think that I don't know what is the coefficient in the form of W1 and what is the constant in the form of W2. I don't know this. Can my system find out the corresponding W1, W2 value? Or you can say the coefficient value or the constant. Can you find out that? Or you can say, can I find out the weight, because X is my input and Y is the predicted output. So can I find the weight in the form of W1 and the bias in the form of W2? Yeah, you rightly heard. Weight and bias is something that we come across when we talk about linear regression. That the weight will be associated with the input. Who is my input over here? X is the input. So W1, which in this particular linear expression or polynomial expression, is what we can say that the 2 is W1, which is the weight that is associated with the variable, or you can say this 2 is the coefficient which is associated with the variable X. We can see that right over here, and 1, which is the constant value in the form of bias. But what if I don't know what is my weight and what is my bias? I don't know. What I know is that I have the following input and I also have the following output. Can my system able to find out the corresponding weight and bias? Can it do that? Well, in this particular program there was no need of, because I have written my polynomial expression directly over here, so there was no need of. But what if the need comes where you have to find out what is the weight, that is in this particular polynomial expression is 2, and what is the bias, that is in this particular polynomial expression is 1. Can my system find out? Can we do that? And that brings us to something called linear regression. Yes, a term that you have always come across in supervised machine learning algorithm in the form of regression, that is the linear regression. And what this is all about, that what we are going to see in this particular segment of the video. So already we saw that we have a polynomial expression or linear expression we have got. Now can we find out the weight and the bias when we just have got the input and the output? Here I have presented the input, as you can see right over here. These were the corresponding input which I have given according to this particular range function, right? And the corresponding output we already saw, what we have come across when we know this particular polynomial expression, that also I have fed in the form of y, right? So now I'm working on the module called NumPy. Why? Because we have to transform this particular array, right, in a form of a NumPy array, so that we can perform a vectorize operation. What do I mean by vectorize operation? Well, see over here, in order to generate the y value, I have to run a loop. In order to generate the y value, I did a loop. So one by one the value came up in the form of a scalar. But when we are going to do machine learning algorithm in the form of linear regression, I cannot pass the individual value in the form of for loop like what we did over here. That is not permissible. So I have to give entire list at one time so that it can perform the operation. For that reason we have to convert this particular list into a NumPy, and it becomes a vectorize list. And then you don't have to pass the for loop, rather it will take the entire data set at one go. So for that reason I have written this particular list within the NumPy array. So you can say a typecasting is happening over here. Great. Now what? Well, by default NumPy array is in form of matrix that will have row and column. So if you talk about this particular polynomial expression, how many features do I have? Only one feature, that is called x. Yes, and these are all corresponding observation for the given feature x. So I have just got only one feature. So you can think that I have got just one column. So this one represent I have just got one column in the form of one single feature. And this particular column has got multiple rows, but I don't want to count the number of rows. I'm asking NumPy, you please count in behalf of me how many rows are there in this particular column, and that's the reason why I'm giving -1. So -1 would do what? It will count 1 2 3 4 5 6 and 7. There are 7 rows are there, that will be counted, and eventually we will get a shape something like 7,1. And what does that mean? Well, that means that we have got 7 rows with 1 column. Would you like to see that? Okay, great. So let me just provide a command line over here so that it does not distract you, and let me run this particular program, and this is Python space linear, and it's a regression, and I hit the enter, and we get to see the shape is 7,1. I hope you understood why this was readed, because we have to convert in the form of a matrix rather than 1D array. So you have to convert this into 2D array with having 1 column and 7 rows. Wow, great. And over here also I did the same thing. Well, in context to the linear regression, the label will just have 1 column, and it will have, like, you don't have the provision over here for multiple columns. You will just have a provision of 1 column. But in case of X, we can come with multiple columns, isn't it? Like X1, X2, X3, these are all different features we can have. That's the reason why we have to reshape it, but as of this is concerned, we don't have to keep it. We just need to find out the respective values corresponding to the individual observation. So for that reason, we don't have to go for reshape in context to the Y, which is my output. Good, very good. So let me uncomment the rest of the line again, and let's start with the exactly what the thing is going to do. I hope you understood what objective am I going to find out in this particular program is that I want to frame this particular polynomial expression where I don't know what is the value of the coefficient, that is 2, and what is the value of this bias. That means this particular coefficient is a weight, I don't know, and this bias is another weight, I don't know. This is what I'm expecting, that can my program show me that if you plot this particular input and if you are providing this particular output, then the corresponding mapping will generate this particular polynomial expression with having this corresponding W1 and W2. Will this particular program be able to figure out that? And that is something what I'm trying to find out in this context of linear regression. Sound interesting, isn't it? Because I'm trying to show you from a different perspective. I'm sure that you have seen linear expression number of times, but the way I'm presenting linear expression is a completely different approach this time. And side by side I'm showing you that how polynomial expressions, right now we are talking about linear because we have just got only one weight, but this could be a multi also when we have got multiple weight or multiple input, like x1 associated with w1, x2 associated with w2, that also can happen. So in short, we have created a reference of type linear regression that will be available if we go for the following package. So this object got created, which is of referring to linear regression, and now is actually where I'm doing the training. So I'm passing the data in the form of fit function x comma y. So remember, x are my -3, -2, -1, and its corresponding y value, that when my input is -3, the corresponding output will be -5. When my input is -2, the corresponding output is going to be -3. When my input is 2, the corresponding output is going to be 5. I have fitted that. So I have fitted all the observation and its associated result also I have given. So think this to be like a training phase is going on, and once the training is done, that means this entire vector gets fitted inside the linear regression. So once the following two vector has been fitted, now what we are going to do, we are going to check whether it has been able to find out W1, which is my weight, and the bias. Is it able to figure out that? So how we do that with this particular object called model dot coefficient, and since we are dealing with right now only one feature, that's the reason I'm targeting 0. So 0 will show me what is the weight associated to the corresponding feature. Remember, we used to call this as coefficient. So what is the coefficient for the following variable? That's what we are trying to find out, and that's the reason why we have a coefficient term over here. So what is the coefficient for the corresponding x, which is my feature, and that we can also call it in the term of slope or weight, W1, whatever you call it. These are all synonym terms. So here we are getting the weight associated to the feature x, and what is the bias, that we are talking in context to intercept, which we can label it as bias over here. So once we have done this, that means this particular model has been able to figure out this particular linear model, right? W1 into x plus b, and these two values we will be able to figure out what is the coefficient, what is the weight, and what is the associated bias. That what we are going to print right over here now. So let me just comment this, and finally if we run my code once again, this time we will see the value 2 followed by 1 we are able to find out, and that means it has rightly pointed out to this particular linear equation. See, 2 is my coefficient, x is what I am inputting, -3 or -2 or -1, plus 1 which is my bias. So these two constant values it is able to figure out with the help of the model that has trained itself based on the following input and its corresponding output. So once the training has been done, now I can just go and test whether it will be able to predict the y value if I just feed only the x value right now, and that's the reason why you see over here -4. Previously I have checked with -3, so I'm going with -4. This is a new observation which I'm feeding to my x, and this is another observation which I'm feeding to my x, and we have just got one column with 2 rows. The system has to count that, and I want to see the y prediction in corresponding to these two observations, had it been successfully done or not. So let me run the code once again to see this time that what output we are going to get when the corresponding equation is 2x plus 1. Yes. So when I feed -4, so -4 into 2 is -8, and -8 plus 1 is -7, and that's what we got it. When we are feeding 4 in context to 2x, so x is 4 and 2 into 4 is 8, 8 plus 1 is 9. So it clearly predicted that my linear regression has learned that the following linear equation is exactly the following one. So that's what the beauty of polynomial in contrast to linear regression. I hope you understood that if we have a linear data like this, -3, -2, -1, and if we have got a linear prediction in the form of -5, -3, then ultimately we will have a linear model, and then we can call it as a linear regression. So when we are having a linear regression, we can have a single feature like this one, x, but it associated weight we have to find out, that what my model did, and the corresponding bias also we have to find out, that also done by my model. And finally it has able to generate the following linear regression, or the following linear function, or following polynomial function, whatever you call it. Ultimately it has able to find out that this particular input and the corresponding output will have the following equation, that is 2x plus 1. And that's what we have seen in the form of 2 and 1 right over here, when in the actual execution I did not provided this following equation, but my linear regression has able to figure out this. So that's how this linear, polynomial and linear regression they are working. Well, again, I have just gone for only one feature in the form of x. I can have multiple feature also in the form of x1, then it will have a w1, I can have another feature x2, then it will have w2, that also can be there, and then we can say that now my linear regression is dealing with multiple features. That can be a subject of my next video. So I hope that this particular video gave you the idea that how polynomial is influencing linear regression. Okay, so let's wait for my next video. Until then, have a nice time. Bye bye.